Okay, we're going to go back to lessons 14, 20, 22, and 23 and pick up some of the things that we didn't do yet. One of those things is talking about the trigonometric functions. Okay, we've talked about functions. They have a domain and a range. They have things that you put into the function and things that come out of the function. Talked about that. And now we're going to talk about some special functions that have to do with right triangles. All right, so these functions, sine, cosine, and tangent, are functions where your domain is an angle in a right triangle. So the things you put into the function are going to be angles in a right triangle. And then the range, the things that come out of the function when you put that angle in, are ratios of the sides of a right triangle. So in our picture right here, we have this angle A in our right triangle. We have, of course, in a right triangle, we have two legs and a hypotenuse. And these sides relate to the angle A in this way. A, little a, is the opposite side to angle A. Little b is adjacent to angle A because it's one of the sides of angle A. And then C is just the hypotenuse. We call that the hypotenuse. So in this particular situation, B is adjacent to angle A and little a is opposite to angle A. So that's how these four things relate to each other. The sine, cosine, and tangent functions have to do with this relationship in a right triangle. So the sine of angle A is equal to opposite, so little a, over hypotenuse, C. So sine is opposite over hypotenuse. That's what these three letters mean. Cosine of A, angle A, is adjacent over hypotenuse. So B over C. And that is what these three letters mean. Cosine is adjacent over hypotenuse. Tangent of A, tangent of angle A, is opposite, little a, over adjacent. And that's what TOA means. Tangent is opposite over adjacent. All right, so this is how the trig functions work. For a while, it may be hard to remember, so you kind of have to come up with some kind of weird little saying or some way to remember what these are. Now, some people they just say so katoa, but that doesn't help if you don't remember that the H's are silent. So, yeah, I don't get that. But if that works for you, great, do it. I use some old horse came hopping through our attic. So sine, opposite over hypotenuse, cosine, adjacent over hypotenuse, tangent, opposite over adjacent. The reason I use this is because it is weird, and the weirder the thing is that you're trying to memorize, the easier it is to memorize. So that's what we're dealing with. So we're going to use those functions to find some missing parts of some triangles. All right, so in example 14.1, you want to find the sides A and B. You have an angle, 36 degrees, and you have the hypotenuse, 6. So you can use these trigonometric functions to find the missing parts. So let's start out by finding side A. All right, so side A, what is its relationship to the angle we have? It is adjacent to that angle because this side, that is side A, is one of the sides of the angle. And then you have the hypotenuse, 6. So the trig function that involves adjacent and hypotenuse is going to be cosine. So the cosine of the angle, 36 degrees, is equal to adjacent, which is A, over hypotenuse, which is 6. So the only unknown we have is A. So we're going to multiply both sides by 6, and that will give us 6 cosine 36 equals A. And the only way to find the cosine of 36 degrees is either to get a hold of a trig table, which is the way we used to do it back in my day, or have a scientific calculator that has the trig functions on it. So I'll show you what a trig table looked like back in those days. So this is a trig table. It's actually a tiny piece of a trig table. Trig tables involve pages and pages. And there are more trig functions than just sine, cosine, and tangent, so there would be more columns. There's another way to measure angles that's called radians, so that would be another column. But anyway, this has the degrees of the angle, the sine, cosine, and tangent. So back in the day when you wanted to find the cosine of 36, you would open up the back of a book with these tables and you would find 36 degrees right here. And then you would go over to cosine, and that would be 0.8090. And you would put that in for the cosine of 36 degrees. But by the mid-80s, when I was in college, most people did have scientific calculators. So I'm not that old, but, I'm just saying. Anyway, so that's how it used to be done. So when we use the calculator, we need to make sure, first of all, that it is set for degrees. All right, this is super important because if you have it set for something else, it's going to give you the wrong answer. So you have that little button DRG for degrees, radians, and grad. And you will right now be using degrees. There will come a time when you will use radians, but now you're going to use degrees. So 36 degrees, and then you hit cosine, and that gives you the value, and then you're going to multiply that by 6, and that will give you 4.85 about. So that is what we will use for our answer. So 4.85 is equal to A. 4.85 is equal to A. All right, so that is A, and then for B, we can use the Pythagorean theorem, but we don't want to do that because A is approximated now. We just chopped off a whole bunch of it. So we don't want to use A to find B. We would rather just use sine because B is opposite to 36. So sine 36 is equal to opposite, which is B, over hypotenuse, which is 6. So we're going to multiply by 6 on both sides. 6 sine 36 is equal to B. And again, we're just going to punch it in the way we did before. That is, you are going to punch in 36 sine, multiply it by 6, and you're going to get about 3.53 for B. And I should have used the approximation sign over here because it's not actually equal to 4.85, it's about 4.85. So those would be the values for A and B. All right, on the next example, you want to find X and M. Okay, so to find X, I'm just going to use the Pythagorean theorem. That's fine. 3 squared plus X squared equals 7 squared. So 9 plus X squared is equal to 49. Subtract 9, X squared equals 40. Take the square root on both sides. You don't need plus or minus because this is the length of a side. It's got to be positive. So that's going to be the square root of 40, which is 2 times the square root of 10. And you could leave it that way, or if they ask you to approximate it to a certain number of decimal places, you could hit 2 times 10 square root, and that would give you about 6.32 for X. So X would be about 6.32. That would be if we approximated it to 2 decimal places. All right, to find M, we have the opposite side to M and we have the hypotenuse, so we can use sine because sine of m. Remember, you put an angle in for the domain for sine. That has to be an angle. And that equals opposite over hypotenuse. And now we have a different situation. Over here, we knew the angle and we were looking for the ratio. Now we know the ratio and we're looking for the angle. This means we have to use inverse sine because we're putting in the ratio and we want to get out the angle. So the way we're going to do this, we're going to use the inverse sine function, which on your calculator looks like sine with a -1 up there. And that means we're going to put in a member of the range and we're going to get out a member of the domain. So this time we're going to punch in 3 divided by 7, and we have to hit equals. And then we're going to hit second function, sine. And that gives us about 25.38. So the inverse sine of 3/7 is going to give me about 25.38 degrees. Okay, now we're going to talk about angles of elevation and depression. Angles of elevation and depression are always measured from the horizontal. You're going to be doing some problems where you're going to be talking about finding the distance between some airplanes and the ground, or from a boat to a lighthouse, or something like that, where you're looking down or you're looking up at an angle and you're trying to figure out distances. And when they talk about an angle of elevation or an angle of depression, you have to be super, super careful that you're measuring the angle from the horizontal. So angles like this or like this, not the angle from the vertical, like this or this. So this is not making sense right now because you haven't seen the problem, but I'm just telling you, this is important. Make sure that you're always measuring the angle of depression or angle of elevation from the horizontal. Okay, example 14.3, a man 6 feet tall is 200 feet from a tree. Okay, so we have a man who is 6 feet tall. He is 200 feet from a tree. All right. And he measures the angle of elevation to the top of the tree as 11 degrees. So he's looking toward the top of the tree, and that is 11 degrees. And we want to know how tall is the tree. So we're looking for that side that is opposite to 11 degrees in this right triangle. And whatever we get for that side, we're going to have to add 6 feet to it because this is being measured from his line of sight, which is 6 feet above the ground. And just notice we are measuring that angle from the horizontal. All right, so now we just need to use our trig functions to figure out how to find this side of the triangle right here. So that's opposite. And we have the 200 feet is the adjacent side. So we're going to use tangent. So tangent of 11 degrees is equal to opposite over adjacent. And now we just multiply both sides by 200. And we're going to punch that into our calculator. Hit 11 degrees, then hit tangent, and then multiply that by 200. And that's going to give you about 38.88 feet. And we need to add the 6 feet to that because we want to measure the tree all the way from the ground. So that's 6 feet right there. What happened to my thing? There we go. All right, so that is, we're going to add 38.88 plus 6, and that's going to give us the height of the tree to be 44.88 feet. Okay, so here is another one with an angle of elevation or depression. An airplane is flying at an altitude of 3,000 feet above the ground. The pilot sights an object on the ground at an angle of depression of 26 degrees. No, that is wrong. That is not the angle of depression. That's being measured from the vertical, not the horizontal. That is wrong. That's the horizontal. That's where that angle should be. So you got to be super careful that you're measuring the angle from the horizontal. All right, so now you've got your triangle. And the question is, what is the slant range from the airplane to the object? And the slant range means this side, the distance from the plane directly to the object, straight line. And that is the hypotenuse of that triangle. So we have the opposite side, and we're looking for the hypotenuse. So that means we're going to use sine. So sine 26 is equal to opposite over hypotenuse. All right, be very careful here. Do not multiply both sides by 3,000. Do not divide both sides by 3,000. What you need to do is get the x out of the denominator. So you're going to have to think of this as multiplying both sides by x, and then dividing both sides by sine 26. So on your calculator, you're going to push 3,000 divided by 26 sine equals, and that gives you about 6,843 feet. So x is about 6,843, we'll say 0.52 feet. Okay, now we're going to talk about rectangular and polar coordinates. All right, rectangular coordinates are the kinds of coordinates that you have used, that you started using when you first learned about the XY plane. And when you want to locate a point in the XY plane, you can say how far over to go and how far up to go to get to that point. So that's the 0.34. It can be written like this, which is the way we usually write it, or now your book is going to start using vector notation sometimes. I wouldn't mind if you didn't use vector notation at all. I prefer that notation because we really are not learning about vectors, and the book is pretty inconsistent about whether it uses vector notation or not. So when you see 3i plus 4j, it just means this. The I is your x coordinate and the j is your y coordinate. So just write it as regular rectangular coordinates. Okay, there's another way to talk about how to get to that point. You can do it using polar coordinates. In polar coordinates, you kind of think of the XY plane as a circle you can go around starting at 0 degrees at the positive side of the x-axis, the right side of the y-axis. So in polar coordinates, first you think about how far you would have to twist around the circle or rotate around the circle. And then you think about how far you would have to go out from the origin to get to that point. And so that distance, which we're really going to call r, not 5, we're going to call this r. And then we call the angle theta. So to get to that point now, you think of it as, first of all, rotating a certain number of degrees from 0 counterclockwise. You're going to rotate And then how far out do you go from the origin? Distance. So to get to this point, so to figure out the polar coordinates for this point, 3, 4, we are going to have to figure out this angle, theta, and r, basically the hypotenuse of the right triangle formed by the 3 and the 4. So we know that we can find r using the Pythagorean theorem. So 3 squared plus 4 squared equals r squared. So 9 plus 16 is equal to r squared. 25 equals r squared. So r is 5, which I already knew, and that's why I put the 5 there. So that's 5, and then we want to figure out the angle we would rotate counterclockwise from 0 up to that hypotenuse. So that angle, theta, we know that the opposite side to that angle is 4, and the adjacent side is 3. So we can use tangent to figure out what theta is. So tangent of theta is going to be 4 over 3. Now, again, this time we have the ratio, not the angle. So we can't punch in 4 over 3 and hit tangent because we're not taking the tangent of 4/3. We are taking the tangent of some angle and getting 4/3. So we are switching the domain and range for this tangent function. So when I punch this into my calculator, what I need to do is take the inverse tangent of 4/3, and that's going to give me theta. So when I punch this into my calculator, I'm going to hit 4 divided by 3 equals, and then I'm going to hit second function tangent. It's going to give me about 53.13 degrees. So that would give me, theta would be about 53.13 degrees. So your book would write this with the radius here, and then they'd put a little bracket like this and put the theta in there. So this would be written as 5 and 53.13 degrees. A more normal way to do it is 5 comma 53.13 degrees, like that. But since we have to deal with this a whole lot, I think we'll probably just use the book's notation, even though I'm not sure how standard that is. So that's polar coordinates. It's just another way of talking about how to get to a point in the XY plane.